8.2 Properties of Exponential Functions, Day 1. This objective is identifying the role of constants in y equals ab to the cx. Between today and tomorrow, or the first objective and the second objective, I think this one is the harder one. All right, let's go ahead and get started. Graphing y equals ab to the x for the absolute value of a greater than 0 but less than 1. Okay, so graph y equals 1/2 times 2 to the x and y equals negative 1/2 times 2 to the x. So you pick whatever x values you want, and look, they used almost my favorite 5, and then they threw in 3. So they went ahead and evaluated those functions for each value of x, and then they plotted the points. The pinkish reddish one, the y-intercept is a, or 1/2. So this is where your a is greater than 0. You can see it's taking off up. It's coming from 0 and it approaches positive infinity. The blue one, the y-intercept is a, which and then a is negative 1/2. Oh, goodness. All right, not just that, but our a value is negative 1/2. It is coming from the y equals 0 for the horizontal asymptote, and it is approaching negative. Y is negative infinity. I should have been more specific. Coming from y equals 0, approaching the horizontal asymptote y equals 0, and the red one would be approaching y is positive infinity, because this one's going up, this one's going down, and that flows with what we know. This 1/2 is positive, so we would expect it to be positive. Negative is negative, so we would expect that to go down. All right, graph y equals 3 times 2 to the x, and y is negative 3 times 2 to the x. Label the asymptote of each graph. All right, so we are going to go ahead and make our t-charts. I'm going to do, I don't like doing the combined, and I know that it was nice and neat for the textbook, but that just was something I was never good at. It would end up distracting me, and I would inevitably mess something up. All right, so I'm going to do y equals 3 times 2 to the x in blue, and then I'll do the other one in a different color. So we have 3 times 2 to the x. So 3 times 2 to the negative 2, 3 times 2 to the negative 1, 3 times 2 to the 0, 3 times 2 to the positive 1, oops, 3 times 2 squared. Okay, you don't have to write these down each time. I just want you to know where the thought process is coming from. A lot of this stuff is done mentally, and you don't think about writing it down. So just to let you know, you can just go ahead and plug that value into the calculator and get your answer. Excuse me. Now, if you are doing this longhand like me, we know that this negative tells us to flip the base. So then that gives us 1 over 2 squared, which is 1 over 4. So this would be 3 times 1/4, which is 3/4, or 0.75. Again, we have a negative here, so that means flip this base. 1 over 2, which is 3 over 2. 2 to the 0 is 1, so this just gives us 3. 2 to the first is 2. 3 times 2 is 6. 2 squared is 4. 3 times 4 is 12. Hopefully you're seeing a pattern develop there. Each of these is increasing by doubling, if you will, because it's base 2. All right, now let's go ahead and do negative 3 times 2 to the x. And hopefully you see a connection. So we have negative 3 times 2 to the x. We've got negative 2, negative 1, 0, 1, 2. All right, so this is going to be negative 3 times 2 to the negative 2. Negative 3 times 2 to the negative 1. Negative 3 times 2 to the 0. Negative 3 times 2 to the first. And negative 3 times 2 squared. All right, again, flip this. So then that becomes 1 over 2 squared, which is 1 over 4. And now we have negative 3 times 1 4, so that's going to be negative 3 fourths. We have negative 1 here, so that means flip this base. So that becomes 1 over 2, and that leaves us with negative 3 over times 1 over 2, which is negative 3 halves. 2 to the 0 is 1. Negative 3 times 1 is negative 3. 2 to the first is just 2. Negative 3 times 2 is negative 6. 2 squared is 4. Negative 3 times 4 is negative 12. So now you can see quite plainly that the values are the exact same if you took the absolute value of them, with the exception of the blue one is the positive. It's increasing, and then the green one is decreasing. Sketching this, now we are going to have all 4 quadrants represented. That is a horrible line. 1, 2, 3, 4, 5, 6. I'm only going to go to 6. 1, 2, 3, 4, 5, 6. 2. That's a horrible scale. 1, 2. Okay, for the blue one, we have negative 2 and 3 fourths. So that's going to be negative 2.75. Yeah, I doubted myself for a second. Negative 1, 3 halves is 1.5, so that's going to be here. 0, 3, 1, 6, and then this 2, this 12 is going to be way up here somewhere. So this is my positive a function. Now the green, we have negative 2, negative 3 fourths, negative 1, 1 and a half, 0, negative 3, negative 1, negative 6, and then obviously that one's way down here. So this one is looking like, oh my Lanta. Holy cow. This is awful. Let me see. Let me see if I can undo that. Yay, I love the undo button. It is my friend. All right, we're going close enough for heaven's sakes. All right, so now we want to find out what the asymptote of each graph is. Well, obviously these are approaching or coming from y equals 0. So the horizontal asymptote in both cases, or just the asymptote, would be y equals 0, okay? Because they are both getting to really close to that line, but they never cross it. All right, let's go ahead and go to example 2. This one took forever, I know, I'm sorry. Okay, now, this is great, but this is something I did not grasp until I was older. So, what I would do is just plug numbers in, evaluate it, and then plot those points. So, worst case scenario, you don't understand this shifting, just use the t-chart, evaluate it, and plot your points. You will get the right answer. It just takes longer, right? All right, so let's go over this part up here. A horizontal shift, y equals abx minus h. So remember that we're going to take the opposite wherever that is because of this negative, is the same as the vertical stretch or shrink, y equals ab to the negative h times b to the x. A vertical shift y is abx plus k also shifts the horizontal asymptote from y equals 0 to y equals k. All right, so this right here, when we have the plus k at the outside of it, that's shifting our horizontal asymptote from y0 to whatever that value is, okay? So let's go ahead and scroll down. So we're going to do graph 6 1/2 to to the x, and y equals 6, 1/2 x minus 3 minus 2. Okay, what they want you to do is to start marking on the paper instead of just pretending like you have imaginary ink or invisible ink, whichever. So we have x and we have our y. Go ahead and do -2, -1, 0, 1, 2. Okay. Now substitute these in to the original function. So that would give us 6 times 1/2 to the -2, 6 times 1/2 to the -1, 6 times 1/2 to the 0, 6 times 1/2 to the 1, and 6 times 1/2 squared. Evaluating these, negative, flip it, so this becomes 2 squared instead of 1 over 2 squared. So 2 squared is 4, so this gives us 24. This tells us to flip it, so this becomes 2 to the first, so 6 times 2 is 12. 1/2 to the 0 is just 1, so 1 times 6 is 6. 6 times 1/2 to the 1, 1/2 to the 1 is just 1/2, so 6 times 1/2 is 3. 1/2 squared is the same as 1 over 4, and that's not going to be a pretty answer. It's going to be 6 over 4, which is the same as 3 over 2. Okay, now here's where the complicated part came in, and where I, as a teenager, would just take my x and y's, and then, my x's, the -2, -1, 0, 1, 2, and plug them into here, and then get my y values, and then plot those points. It did take longer. It did. There's no two ways about that. Okay, what this means, this is a horizontal shift. And if we go opposite of the sign. So we're going to go not 3 to the left, we're going to go 3 to the right. And this -2 tells us that we are shifting the horizontal asymptote down 2 units. All right, so here's how this plays out. All right, you can either come over to your original T-chart, and you know that you are going 3, never mind. Almost made a mistake there. Let's go ahead and, whoa. I was going to say something else, but I am not. All right, so let's go ahead and graph the original, and one, two, three, oh my goodness, 4, 5, 6, 7, 8, 9. Why did I do that to the negatives? I don't know. 6, 7. Good enough. Okay, so we're going to come over here and plot the points. So -2 and then 24 is way up there. Not going to worry about it. -1 and 12 is, again, way up there. I'm not going to worry about it. 0 to the 6, so we go 1, 2, 3, 4, 5, 6. But we know it's coming from up here somewhere. 1 to the 3rd, or 1 goes to 3. 2 goes to 1 1/2. All right, now rather than drawing my curve, I'm going to go ahead and do my translation of the graph. We're going to go 3 units to the right. So this is going to go from x is 0 to 1, 2, 3. And then we have to go down 2, so I don't know why I did that. So we would go down, we go right 3, 1, 2, 3, and then we go down 2, 1, 2. This one we go 1, 2, 3, and then we go down 2. 1, 2. Here we go, and we're at -2, so 1, 2, 3, and then we go down 2, which is going to take us down here because that's at 3 halves. So there we go. So if you are, this is just a horribly graphed points. This one's over way too far, and that one was over way too far. That's a little bit better. This one is way up in the air, so that's why that one just, it is much better if you have grid line paper. Yes, I would agree. All right, so here is our translated. That's a word from geometry, taking it back a little bit. Oh, I am not going to win any awards for my graphing abilities. That's for sure. Oh my goodness, I don't know what's going on. All right. Oh, for heaven's sakes. Guys, I promise you I'm not doing that on purpose. Okay. Let me pull this down a little bit. This is example 1. Where did example 2 go? Oh no. Undo. Sorry. All right. Jeepers. Oh, welcome to the world of Conover, right? All right, so here is the original graph, and it's going to be approaching y equals 0. The translated function is going to be, ooh, jeepers. The horizontal asymptote here is going to be y equals -2 because we've moved that down 2. All right, that's it for example 2. Oh my goodness, this is taking forever, and I'm sorry. Example 3, we're visiting Technetium 99 again. Going back to chapter 7, we haven't worked with it once, I think. If not, I'm confusing you with algebra 1. Since a 100 milligram supply of Technetium 99M has a half-life of 6 hours, find the amount of Technetium 99M that remains from a 50 milligram supply after 25 hours. Okay, so well, we're going to have to convert that. So in this, oh, geez. All right. Find the amount of Technetium that remains for a 50 milligram supply after 25 hours. All right, well, the decay rate, I was trying to think of the easiest way to explain this, and I don't see anything up there. The decay rate is going to remain constant throughout this function. Otherwise, it's not a function. A half-life means that your decay rate is b equals 1/2, which is 0.5. And in this case, your starting amount is going to be not 100, but you're going to find it in 50. All right. Now, here's the kicker. It has a half-life of 6 hours, and we want to know what it is after 25 hours. So we're going to take the x, and we need to divide 25 by 6, because that's going to be the number of times it breaks down. All right, using the calculator, 25 divided by 6 is not going to be a pretty number. 4.17, right? So let's go ahead and get that on there. So x is 4.17. Right. Writing the equation, we have y equals ab to the x. So that's going to be 50 times 0.5 raised to the 4.17. There is no way I can do that in my head. All right, so 50 times 0.5 raised to the 4.17. And that gives us 2.77. So after 25 hours, we have approximately 2.78 milligrams remaining. Okay. Hopefully that helps. I apologize for examples 1 and 2, but again, remember you can fast forward. Have a great day.